Hi. In the previous segment, we looked at ways of defining sets and operations on pairs of sets. In this one, we shall discuss working with multiple sets and also the concept of a power set. We often define not only one single set, but a whole collection, in fact, a whole set of sets that are related to each other in some way. We call such a set of related sets a family of sets. In many cases, the sets of a family are distinguished by an index. All indices taken together form the index set of that family. For example, let us take a look at a group of people, P. If we wanted to study their romantic interests, for instance, we could, for each person in P, list the people that person has at some point had a crush on. For example, Charlie was interested in Violet, the little red-haired girl, and Peggy. Lucy was interested in Schroeder, and Violet in herself. Admittedly, it is a bit of a stretch to classify Violet's infatuation with her curly hair as a romantic interest, but it's all for the good cause of illustrating a mathematical point. Taken together, these sets of romantic interests of the various people in P form a family indexed by the elements of P, that is, by the individual people. Now take a look at this set definition. Determine its extension and then interpret it in terms of romantic interests. The extension is Sally, Linus, and Violet. The interpretation is that it is the set of those people in P whose romantic interests in someone else in P was at some point reciprocated, though not necessarily at the time they were interested in that person. Working with families of sets is especially useful when those families are very large, or even infinite, such as in these examples. What do these sets mean? And by this I mean not the extensions, because they are infinite anyway, but rather their interpretation. Ni is the set of all natural numbers greater than or equal to I. Mi is the set of all non-negative multiples of I without I itself. And di is the set of all divisors of I without I or 1. So with this, what then is this set? It denotes the prime numbers. It's the set of all integers greater than or equal to 2 who don't have divisors other than 1 in themselves. With sets of sets, we can generalize the union and intersection operators. Let's suppose S is a set of sets. Then the generalized intersection over S, which is denoted by this large inverted stylized U, is the set of all elements that are contained in every set in S. The generalized union over S, denoted by the large stylized U, is the set of all elements that are contained in at least one set in S. When S is a family of sets indexed by an index set, then often one of these notations is used. Things sometimes become a little surprising when computing the union or intersection of infinitely many sets. Consider this example. Here Q is the set of rational numbers. As you can see, the AI are intervals in the rational numbers from 0 to I 1 minus 1 over I. Think about the following two questions. For each I, what's the biggest number in each AI? And B, what is the biggest number in the generalized union over all AI? As the individual AI are these closed intervals, the largest element in each of them is 1 minus 1 over I. And so the set we're looking at in the second question is the generalized union of an infinite number of these closed intervals. Each of these intervals contains a greatest number. However, the union does not contain a greatest element itself, meaning that is open to the right-hand side. The reason is that 1 itself is not an element of that union, simply because it is not an element of any of the sets participating in the union. All numbers below 1, however, are in the union. Therefore, an infinite union of closed intervals produced an interval that is open to one side. Now on to power sets. Given a set A, its power set is the set of all subsets of A, including A itself and the empty set. It is represented as P of A, or sometimes also as 2 to the power of A. For example, the power set of the empty set is a singleton set containing just the empty set, because the empty set is the only subset of the empty set. The power set of a singleton set, containing A in this case, is the set of the empty set and the singleton set itself. The power set of a two-element set, AB, contains the empty set, the set itself, and also the two singleton subsets of it, and so forth. Every power set contains the empty set and the set itself. Also, for any set A, the cardinality of its power set is 2 to the cardinality of A. Try to test your understanding of this by developing an intuition for why this is the case. And for now, it's probably a good idea to limit this only to the finite case. Power sets have an interesting regular structure that becomes visible in what's called the Hasse diagram of the inclusion relation of its elements. In a Hasse diagram, we arrange all the elements of the power set, in this case of the three-element set ABC, and connect them in such a way that an upward edge means that the higher set includes the lower set in the diagram. Also, we omit all edges that are implied by transitivity. For example, the set containing A is a subset of the set containing ABC, but there's no edge between them, since that edge is implied by transitivity by the edges between A and AB and AB and ABC. In this segment, we looked at sets of sets and extended union and intersection to them. and noted what happens when operating on an infinite number of sets. And we also learned about power sets. The next segment shows by way of illustration how the things we have talked about so far can be used to define the natural numbers.